All right, I think it's 10 o'clock. We'll give folks a couple minutes here to join. There's generally 50% of the audience that takes about 2 to 3 minutes past the hour. So I'll let that happen and then swoop back in. Thanks for joining me for those on time. Appreciate it. For those joining, we'll just give a couple more minutes here. Get started at 10:02. Hold on to your lug nuts because you are in for 40 minutes of the most thrilling AI ride of your life. Just kidding. Pretty fun stuff, though. It's also Thursday. Thursday is the new Friday, for those that don't know. All right, 10:02. Let's get started, shall we? So just by way of introductions, I'm Tim Freestone. I'm the Chief Marketing Officer over here at Kiteworks. And today's presentation is about AI, as most presentations these days are in one form or another. And we're going to talk about its evolution, its impact, and its impact on cybersecurity decisions. So they say that when you give presentations or do public speaking, you either start with a story or a joke. And for those that know me, I usually start with a joke, and I try to make it the worst joke I've ever heard so that others can feel that pain. What's good about jokes these days is I can go to AI and ask them for a joke relevant to my presentation. This time I went to Claude, and Claude did not disappoint. This is a terrible joke. So I asked it for a joke about AI. Here's the joke. Why was the robot angry? Anyone? Because someone kept pushing its buttons. That's terrible. Anyway, let's get started, shall we? So I'm going to take about 70 years of evolution and condense it into about 5 slides. So without a doubt, I've missed a lot of things, but I've tried to kind of highlight some of the pivotal moments in the past 73 years-ish, and really just to kind of reinforce that AI isn't new by any stretch of the imagination. It's been being worked on for quite some time with ebbs and flows. We're just in a compounding interest of innovation right now. So just to take you in the way back machine, we're really talking about the start of AI and being in the 1950s. And there are really 3 key events in the 50s that represent the birth of AI. First, in 1950-ish, Alan Turing published his famous paper, Computing, Machinery, and Intelligence. And this is the paper where many of you have probably heard of what's known as the Turing test, which is a way to evaluate whether a machine can be considered truly intelligent. And the net of it is, if the machine can answer questions or communicate with a human without that human knowing it's a machine, it passes the Turing test and therefore is intelligent. The second, in 1955, was really when the term artificial intelligence was coined. And now that it had a name, I'm in marketing. Naming something is 50% of the battle. Now it had something to springboard off of as a category. Then in 1956 is really when the first sort of organized conference was known as the Dartmouth Conference, which was organized by John McCarthy and a few others, which was focused specifically on artificial intelligence research. And the whole purpose of the conference was devoted to advancing machines to solve the kinds of problems that were then reserved for humans. And so in summary, the 50s were essentially the birth. There's some arguments of being before that, but for the purpose of this presentation, from Alan Turing to John McCarthy and his conference, what we saw happen in the 1950s. So then we get into the 60s and we start to see more progress happening. First, you started to see programming languages come out in 1958, again developed by John McCarthy. A programming language called Lisp began, which was focused on developing artificial intelligence. Second, you started to see research into neural networks expand in the 60s. And for those that don't know, neural networks are kind of the brain processing of artificial intelligence. Research scientist named Frank Rosenblatt developed what was called the perceptron algorithm for neural networks. And this showed the first promise of pattern recognition tasks. Third, there were new centers and conferences for AI research that were established to provide essentially more structure. There was the Stanford Artificial Intelligence Laboratory in 1963, and then many more AI conferences. And then finally, we see early intelligent robots being built. This one's my favorite. Its name is Shaky, the robot, which probably shows how much confidence they had in this robot to do any sort of tasks. But essentially, Shaky could perceive its environment and navigate autonomously. Kind of reminds me of my Roomba, although that only got good like last year. So then following the 60s, there's some progress in the 70s, but mid to late 70s and in the 80s, you start to hear what's called the AI winter, which is when sort of interest in artificial intelligence started lagging. There was something called the Lighthill Report in 73, which criticized the general lack of progress. And that spearheaded some real decreased lack of funding. Books like Hubert Dreyfus's What Computers Can't Do critique the limits of AI. Early AI systems were essentially pretty limited. They struggled with things like automating translated languages, and they just took longer than expected. The rise of the systems that were attempting to simulate human expertise, building and maintaining them was incredibly expensive, very difficult. And then the US government ultimately started decreasing defense spending on AI in the late 70s and the early 80s. So lots of things were coming together where it looked like the 50s and 60s progress was a flash in the pan. And ultimately, overall funding dried up. And that was why they called it the AI winter. So out of the 80s, a lot of trends, bad trends stopped at the end of the 80s, music being one of them. But into the 90s was really when we saw a resurgence. After the AI winter, we saw new machine learning algorithms that were created to analyze large data sets. Those machine learning algorithms could make predictions without needing explicit programming. Advancements in neural networks, vector machines, and what they call ensemble methods like random forest came into play. And then secondly, we started to see increased computing power. And as we all know, computing power is really the driver, which we'll get to more in a moment, on the effectiveness or the usability and real life applications of artificial intelligence. Also, in the 90s is when machine learning started to be applied to real world problems, not just in academic circles. Machine learning was started to be used for optical character recognition, speech recognition, data mining, lots and lots of stuff. Obviously, the internet had a big role. The democratization of the internet had a big role in AI, and of course, with the need for sharing of data and sharing of machine learning models, essentially the open source of knowledge. And then finally, even more conferences started coming out, journals dedicated to AI machine learning. There was the conference on neural information processing systems, which really kind of cemented machine learning in the 90s. Now into the 2000s, promise we'll get out of this timeline here pretty soon, but it's important to get context. In the 2000s, there was really the explosion of big data, massive data sets, and the machine learning algorithms to go along with those data sets started to appear. Again, data, yes, it's the new oil, has been for 20 years, but the amount of data that was started to be produced in the early 2000s made it more realistic to apply machine learning and AI to real life requirements. Second, deep learning sort of came onto the scene with a vengeance. Maybe 4 or 5 months ago, you might have remembered the name Geoffrey Hinton being on the news, coined the godfather of AI. As we can see, there were a lot of other people before him that were instrumental in the development of AI, but his work on deep learning was critical. Third, there was advances in computing power, particularly GPUs, which graphics processing units, which were built mainly for gaming computers essentially, but it was obviously quickly transposed onto artificial intelligence and deep learning models, and that increased the computational speed that allowed AI researchers to develop bigger systems capable of tackling much larger problems and computations. And then once deep learning started to get into big data analytics, and how companies use data to make decisions started to become incredibly important from a competitive advantage. And deep learning and big data analytics started going hand in hand. So you started to see more applications of deep learning in the use of big data, or big data analytics. So the 2010s, we saw essentially the transformative decade, although probably when we get out of this decade, we'll probably say that about the 2020s. But the 2010s was when things like the breakthroughs of deep learning in gaming happened. So it was the first time an AI system beat a professional Go player. It was in 2016. Also, when we started seeing a revolution around self-driving car technology, there was the birth of natural language, NLP, natural language processing. One moment, I take it. Drink of water. At least you know it's live. And this was where you started to see the release of large pre-trained models like Elmo, BERT, and GPT-2 in 2018. In 2019, OpenAI, to continue the gaming challenge, became the first AI system to defeat world champions in the complex video game Dota 2, which Go is one-on-one, Dota 2 is multiplayer. You have to be incredibly dynamic in your decision making and take in the potential paths of multiple players versus one. So that was a big leap. And then essentially at the end of the 2010s, we started to see a lot of proliferation across different industries like medical diagnostics, started to see that helping to design novel proteins, producing art, etc. And then really we're at kind of where we are today. And we'll talk about this statistically just to kind of drive home a point. So in the last few years, one of a recent study by PwC shared that because of everything that's happened in the last 70 years, but really the last few years, 52% of companies have now accelerated their AI adoption plans coming out of COVID. As of 2023, 35% of companies are using AI and 42% of companies are exploring AI implementation for the future. And if you look at the global artificial intelligence market size, it's projected to grow from 150 billion, already pretty big, to 1.345 trillion by 2030. That's a T, and has a compound annual growth rate of 36.8%. So when you see the news or the media talk about the AI gold rush, that's a thing. So we're going to transition now from a little bit of where we were, where we went, and where we are to kind of what's driving, what's behind the effectiveness of all of these AI systems. And it's sort of the first time, at least in my experience, where unstructured data becomes a significant driving force in some sort of evolution, at least within technology. So and unstructured data is what I'm talking about is essentially content. That's pretty numerous in terms of forms. You've got emails, videos, files, server logs, social media posts, anything as the name might allude to that's not structured. And there's some recent reports lately that it's estimated that between 80 and 90% of the world's data is unstructured. That's a lot of data. That this type of data is growing at a rate of 55 to 65% per year, which is estimated at 3 times faster than the growth of structured data. And furthermore, the research firm ITC predicts that the volume of unstructured data will grow from 33 zettabytes, as it was in 2018, to 175 zettabytes in just the next year and a half. So lots and lots and lots of unstructured data, which is definitely the most challenging to organize, to manage, and to secure, because a lot of companies are going through this e-discovery phase right now just to find where it is. You have to, once you find it, you have to classify it. Once you find and classify it, you have to control the new data that's being built while classifying and discovering and classifying it. And then you have to protect it all. So tracking, controlling, and protecting all this unstructured data is incredibly important. And then you insert large language models into the picture, as if it wasn't hard enough without these systems that are just beasts for unstructured data. So according to another survey, it showed that 53% of data scientists and engineers plan to deploy a large language model into production in the next 12 months or as soon as possible. And we've been seeing these large language models integrated into many business applications, marketing, software engineering, customer operations, R&D, et cetera. One second. Excuse me. In the fintech industry alone, the market for AI is expected to expand at a rate of 28.6 and reach 31.71 billion in 2027. And in a recent survey of over 1,000 companies with more than $1 billion in revenue, 67% saw it as a top priority to adopt LLMs and generative AI. So massive explosion of unstructured data, massive growth in large language model systems that consume unstructured data for training, for knowledge bases, and use unstructured data formats for querying through prompting. That's quite the cybersecurity nightmare, to say the least. So I talked a little bit about massive data sets for training. LLMs are essentially characterized by by two main aspects. So what's called the number of parameters and the number of tokens that are used in the training data set. So parameters are essentially the factors that an AI system uses to learn, or AI system learns from its training data, and then uses those parameters to make the prediction. So ingest what the action is or what the request is and provide the answer and make the predictions on what's actually being asked and what should be answered, and essentially shape the whole AI, understanding of the AI. And it processes, most of the LLM systems have billions of parameters. So for example, GPT-4, which is the latest one developed by OpenAI, is estimated, don't kill me for those who know that kind of the answer is a guess, but around 1.76 trillion parameters. And again, this is a closed system, so the amount is somewhat speculated, but you can actually go to open source systems like Falcon 180B and that, or Meta 2, which are in the hundreds of billions of parameter. Falcon 180B earned its name from 180 billion parameters. So that's parameters. Tokens, on the other hand, are the units of text or code that an LLM uses in processing and generating the language. So those can be characters, words, words, segments, code, text, anything that is essentially unstructured and can be tokenized for the method of the model that the model uses in its scheme. And the amount of tokens used in training and the amount of parameters really kind of combine to give you the effectiveness of the AI system. And GPT-4 is trained on approximately 13 trillion tokens, and Falcon 180B, I think, is around 4 trillion tokens. So lots and lots and lots of data going into these systems. And this is what essentially enables them to generate human-like responses. So all of that evolution from the 1950s to the last few years, computer processing, the GPUs, the large amounts of data sets, the neural networks, lots of smart people in a small room for several years produce what we're looking at today. Sorry, I forgot the animation on that one. So now let's get into what this means problematically for the industry after I take another drink. So number one, data leakage. Large language models can inadvertently expose a company's sensitive data in several ways. And you've been paying attention to the news at all. This started, I think, with Samsung, but I can guarantee you hundreds of thousands of employees across tens of thousands of companies right now are accidentally dumping sensitive information into prompts and or backends of large language models. So first, for training data, again, all that data that gets tokenized and used in the training of the system, that can contain proprietary information, customer data, confidential details, if not properly filtered. There was a recent news study where some engineers, some research scientists or engineers, one of the two, at Microsoft accidentally dumped like 3 trillion or 3 terabytes of sensitive information into one of their models. Second, the model's responses can reveal parts of the training data that you don't want to be revealed. So attackers can probe large language models with different types of inputs and prompt injections to extract data that you didn't want to, or companies don't want to be exposed. Third, whole models can get stolen with all of the training data in it. So you have to protect the perimeter of where the model is operating. If an adversary steals an entire model with the training, the data, that can be very valuable in the competitive landscape. And then finally, the APIs that run through all these systems. I think you're gonna see a resurgence of API security. Companies like, I forget the names of several, but there's a lot out there. Used to be a former life of mine. Trying to protect APIs so that adversaries can't essentially breach an API and get into data flows. The other thing that companies need to be concerned about is data poisoning. This is a pretty big deal. Essentially, attackers can manipulate training data to degrade the model performance or create vulnerabilities within the model itself from the training data. Things that could happen is bias could be inserted to skew certain prompt answers to one outcome or another. It's a little softer of an issue, but also poison data can be used to implement backdoors, which attackers can enable. Backdoors have been around for a very, very long time, but once you get in through a backdoor, you're then in the data itself, and essentially you could be in the network. And depending on where that large language model sits, whether it's single tenant or multi-tenant, could adjust privileges and go into other data sets within that server. And so we're seeing sort of a number of things already start around the challenges that this new application system poses to cybersecurity professionals. But just to kind of double click a little bit on model theft, pretty interesting. An attacker can infiltrate a network that's hosting a private model, or just exploit some vulnerabilities that might be in the model, and even use insiders can access the model who shouldn't, depending on privilege access. But once they steal it, they can freely replicate, they can modify it, they can deploy models for malicious purposes. And one of what it's starting to become apparent is that stolen models with data can be used for social engineering. So data that's personal on certain people can be used to create social engineering attacks that seem really real because of the knowledge they have about the person that they're attacking. So these are entirely new vectors for the bad guys and gals to go through that are certainly top of mind. And let's not forget about the auditors. So tons of regulatory compliance risk here. Again, even traditional application security, traditional network security, with the occasional exception of just outright sabotage, those security systems are meant to protect the data. It's the data that's the important thing. That's where all the information is. So you have all of these compliance regulations that are focused on proving that the data, the PII, all of this information is safe. Now, the GRC teams, the privacy officers, they all have a whole new system. They didn't even catch up with what was happening in the past 10 years. They're a whole new system of concerns. I got a text this morning. We're at the IAPP conference in San Diego today, and this is the #1 topic at that conference. So compliance is going to be a big issue, or is a big issue, I should say. The other thing for companies, especially in manufacturing, IP infringement, huge problem, right? Trade secret protection is crucial for maintaining a company's competitive edge. However, an employee might input a trade secret into an AI prompt. Researchers, engineers might accidentally put in trade secrets into the training data. Again, familiar points of entry, but once that data is in there, it's in there, and it can get accessed. Essentially, employee negligence is found another home, and it sort of in the end, data governance, IT protection, they're just really essential to protecting IP loss. And because AI is based on significant data use, it increases the opportunity for that IP related data to get ingested one way or another. So, problem spelled out, right? Hopefully, data, model theft, privacy problems, compliance, things like that. So how does the industry address this? First, they drink water. Once you drink some water, you start going down the gambit of options. One of them, privacy enhancing technology, relatively new, PETs. They're pretty critical. There have been some discussions about how privacy enhancing technologies can impact performance. But there's a number of ways that this privacy enhancing technologies can be used. One is differential privacy, which adds sort of a noise to the data sets to prevent the models from memorizing personal details. Federated learning allows models to be trained on decentralized data from users, so different data sets, different sources. And then the final one is homomorphic encryption, which is encryption on data while it's being computed. That's really where I think a lot of the performance hits actually happen. The other layer to this is what's known as confidential computing. So it essentially allows sensitive data to be processed in isolated environments, which they call trusted execution environments, or enclaves is another word you might hear a lot more of. And in those enclaves, data remains encrypted even during processing. So CPUs or GPUs need to historically need to decrypt the data to process them. Theoretically, in confidential computing, it protects against that. And just overall, look, confidential computing is essential, but it's got to be deployed throughout the whole life cycle, training and during the deployment of the AI. Again, during training, it ensures that the data sets remain encrypted and are not exposed to the model developers. And then once deployed, it protects queries and model outputs, preventing data exposure. PETs, confidential computing, relatively new to the scene. And obviously data encryption isn't, but they bring that to the table. But what really needs to start happening in the short term are controls. And this is the tale as old as time. So you really got to start reducing the risk of data loss through controlling and continuously monitoring and auditing what's happening. It's really indispensable for AI systems. And there is sort of a roadmap that you can use, which is a similar roadmap that has been deployed for monitoring and auditing unstructured data sets and the use of unstructured data in applications over the past 15, 20 years. One, obviously, you need to choose the metrics that you want to track. Going to go through the roadmap here a little bit. You got to monitor the prompts. So companies are deploying internal systems using both closed AI large language models like Claude or OpenAI's ChatGPT-4 systems, but putting prompt GUIs on the front end so that they can monitor who's logged in and who's prompting what. You need to implement human in the loop functionality. Sort of never trust, always verify. People are still very important. So if then show to is a step that needs to happen in securing AI systems. Also, there's a lot of data moving, a lot of people using them in organizations. So applying automation and AI to the actual process of continuous monitoring, auditing is incredibly important. Also, scalability. If you have a company that's got tens of thousands of employees that you're trying to use this system, you have to be able to scale for different cloud-based solutions with your security infrastructure on the AI LLM system. And then finally, just conduct regular audits. So yes, you're monitoring, but what's the audit structure you have on the training data that's happening? How often are you looking at it? What are you looking at? How to identify issues? And that is in the training and even the fine-tuning process, as well as the prompting. So continuous monitoring and auditing is incredibly important. Encrypting sensitive data. We talked a lot about sort of real-time or in-use encryption with PETs and confidential computing. But remember, much of this data is unstructured on the onset. So encrypting files and data that's going to be used by the systems before they use them, encrypting data in use, encrypting it as it's in transit are very important. So some of the roadmap stages for this: identify and classify your company's unstructured data before it's used in systems for training, fine tuning, and for the knowledge base. Get it into a technology that you can monitor and audit it. But when it's sitting in the depot, make sure it's encrypted. You have to do this across file level, disk level, as well as in transit, using encryption like SSL or TLS, what we call double encryption. And obviously, you need, with the classification comes what gets encrypted, what doesn't get encrypted. And then leveraging access controls across key management and what can get decrypted with privilege access management, starting to talk a little bit more about zero trust in these systems, and then monitor all of it and keep detailed audit logs of what gets encrypted, who decrypted it, where it is. The encryption requires the monitoring and auditing as well. So with least privilege access, it's a critical controls for security integrity. Least privilege access to unstructured data, as I talked about in a moment, super important. You have to carefully control what data the models can access during the training and inference. You have to apply zero trust because there's sensitive data all over that, as I spoke to ad nauseum, PII, PHI, financial data, etc. Apply role-based access controls that should be implemented so that only the right users can process or get access to the data that's absolutely needed to train, fine-tune, and prompt your enterprise LLM systems. And then again, continuously monitor the access. So you're monitoring the flow of data, you're monitoring the encryption of data, and you're monitoring the access of the data, and auditing all of those within the LLM system to ensure the lowest risk possible. And then finally, am I finally? Yeah, finally. So just under 40 minutes. How do you pull all this together? Well, I talked a little bit about privacy enhancing technologies and confidential computing. Those are certainly systems worth layering in, but to the degree that you can find something that will help you at least get started in this very immense roadmap to secure large language models, that'd be fantastic. Luckily, Kiteworks is positioning ourselves in this model around continuous monitoring and auditing, encryption, and least privilege access. It's what we've been doing for 20 years, people to people, machine to people, machine to machine, unstructured data in use, in transit, at rest. AI LLMs are simply a new machine. They've got APIs, they've got database knowledge-based storage. They just have a new way of using all of that. So applying the types of things we talked about, or I've talked about in an LLM, has its nuances to be sure, but fundamentally, we're still talking about the movement of unstructured data from fine-tuning and training to prompting, and then in between the flows across the parameters that are deciding what to say when, and the knowledge base of where the data is. So as you go through your journey with your company, I'd invite you to talk to Kiteworks and invite us to go on that journey with you. Everybody's exploring. We're all in this sort of design partner relationship here as an industry. And we are starting to, as a company, experimenting with our own internal AI systems, using Kiteworks to do everything that's on the screen within our own internal AI systems to make sure that we're the cobbler with repaired shoes, not holes in the shoes. So lots to cover, 40 minutes, give or take. Appreciate your time. If you have any questions, I think there's a Q&A module in this, but also you can shoot me an email afterwards. It's tim.freestone@kiteworks.com, and appreciate everyone's time today. Have a great rest of your week. Enjoy your Friday.